Okay, so now I'll be talking about HTTP traffic. And HTTP stands for Hypertext Transfer Protocol. And it is a commonly used port for the World Wide Web and used by some websites. And HTTP is used to send, get, and post requests to a web server in order to receive things like web pages. And knowing how to analyze HTTP can be helpful to quickly spot things like SQL injection, web shells, and other web-related attack vectors. And it is one of the most straightforward protocols for packet analysis, and the protocol is straight to the point and does not include any handshakes or prerequisites before communication. So I'll be opening a HTTP packet capture file. So to demonstrate what I mean, okay, so this is a sample HTTP capture file, as you can see. And we can navigate deeper into the packet capture by looking at the details of one of the HTTP requests, as you can see here in packet 4. So yeah, this is how the HTTP request looks like, but I'll be explaining deeper. So as I go on, and looking at this packet, we can identify some very important information like the host, the user agent, the requested URI, and the response. So we can use some of Wireshark's built-in features to help digest all of this data and organize it for further analysis. So first, I want to organize the protocols present in the capture using the protocol hierarchy option. And for that, I go to statistics and click on protocol hierarchy. So as you can see, this information helps us, is very useful in practical applications like threat hunting to identify discrepancies in packet captures. So you can see the percent packets of TCP is 95.3, and for HTTP we have a 9.3. So yeah, that's it for the protocol hierarchy. Another feature we want to look at is the export HTTP objects. And for that, we go to File, Export Objects, and we click on HTTP. So this feature will allow us to organize all requested URIs in the capture. So that's the function of the export HTTP object. So as you can see. And finally, the last feature we want to look at is the endpoints feature. For that, we go to statistics and we'll click on endpoints. And this feature can be useful to identify where a discrepancy is originating from. You can just click on the IPv4, it shows us the IP addresses and the amount of packets that are coming from an IP address. So that's the function of the endpoints. HTTP is not a common protocol to see too much, as HTTPS is now more commonly used because HTTPS is the secure version. But HTTP is still used often and can be very easy to analyze if given the opportunity. So before I go, I want to answer some questions that are for this packet I opened, this packet capture file. So the first question here is what percent of packets originate from domain name system? And for that, we need to use the protocol hierarchy option. And for that, I navigate to statistics and I click on protocol hierarchy. As you can see, the percent packets of DNS is 4.7. So if I go back to the question, the answer to this is going to be 4.7, question 1. And they say what endpoint ends in .237. So for that, I use the endpoints. So again, go to statistics, endpoints, oh, IPv4. So this is it. This is the address that ends in .237, which is 145.254.160.237. And the next question is, what is the user agent listed in packet 4? So we'll go to packet 4, which is this. As you can see, this is the user agent right here. This Mozilla slash 5.0, like, yeah, this whole role is the user agent. I'll go to the next question. So it's looking at the data stream. What is the full request URI from packet 18? So we'll go to packet 18. And we'll scroll down. Okay, so this is the full request URI. This row here. That will be the answer to that question. We have question 5. What is domain name was requested from packet 38? So we go to packet 38 and we export the object HTTP. Okay, so this is packet 38. We can see what was requested, which is www.ethereum.com. That will be the answer to that question. And lastly, looking at the data stream, what is the full request URI from packet 38? So packet 38. Yeah, this is the request URI here, which is this http://ethereum.com/download.html. So that's it for HTTP traffic. Thank you for watching, and I hope you enjoyed it. Okay, now I'll be talking about HTTPS traffic. And HTTPS is the secure version of HTTP. What this means is that information is encrypted over the network with HTTPS. So before sending encrypted information, the client and the server need to agree on various steps in order to make a secure tunnel. And here are the steps. First, the client and the server agree on the protocol version. Next, the client and server select a cryptographic algorithm. Third, the client and the server can authenticate each other. And lastly, the client and server create a secure tunnel with a public key. So I have a packet capture file, so we can see an overview of the HTTPS traffic, and let me just open that. Okay, as you can see on our screen, this is an overview of how an HTTPS traffic looks like. And if we look at packet 11, yeah, we'll see the application data. And taking a deeper look, you can see it's encrypted, which is this. So if it was an HTTP traffic, it will be, we're able to see the application data from here, but since this is encrypted, we can't see, we can't understand what's being sent on the network because this is HTTPS. So we can begin analyzing HTTPS traffic by looking at a packet for the handshake between the client and the server. If we take a look at packet 4, this is a client hello packet, and it shows the SSL v2 record layer, which is this. It shows the handshake type and the SSL version. And looking at packet 6, we can see the server hello packet. This sends similar information like the client hello, but this time around we can see the session details, which is the session ID length and the session ID itself. And we can also see the SSL certificate information. So this is the certificate information here, as you can see. Then if we go a bit further to packet 8, yeah, we see this part of the handshake will determine the public key used to encrypt further messages between the client and the server. So let's take a look at it. As you can see, this is the client key exchange. We also see the handshake type. We also have the SSL v3 record layer. We have the SSL version. As you can see, this is the encrypted handshake message. And in the next packet, which is packet 9, the server will confirm the public key and create the secure tunnel. So all traffic at this point will be encrypted based on the agreed upon specifications listed above. So this makes the traffic between the client and the server encrypted, and we'll need the secret key in order to decrypt the data stream being sent between the two hosts. Okay, so now I'll be demonstrating how we can use an RSA key in Wireshark to view the data unencrypted. So pay attention to the application data in packet 11 and packet 21, because when I decrypt it, we'll be able to read the application data. So first I need to navigate to the protocols, and for that I go to edit, preferences, protocols. So here, if you're using an older version of Wireshark, you can select SSL. But since I'm using a newer version, I'll select TLS, which is the transport layer security. So yeah, so I need to click on edit, then add and input the IP address. For this demo is 127.0.0.1. Then the port is going to be start TLS, start underscore TLS. The protocol is going to be HTTP, and the key file. So yeah, we need to locate the folder for the key, and just go to my downloads. So this is the key here. So I open it and I click on OK. Okay, now that we've imported the key into Wireshark, the RSA key into Wireshark, if we go back, as we can see that the data stream is now unencrypted. So this is packet 11 and packet 21 from earlier. We can see now that we now have it like an HTTP traffic where we can analyze the application data. Okay, so now if we scroll down, we'll see, yeah, this is the HTTP traffic now that has been decrypted, and now we can see the user agent, we can see the host for the application data, and we can see the request URL. So this is how we can decrypt HTTPS traffic using Wireshark.